The first to say how the instant must change was the Nobel Prize from Holland, Hendrik Lorentz. Our colleagues from the Netherlands will explain us this.
Okay. Hendrik Lorentz was born in Arnhem, Netherlands, on the 18th of July in 1853. He studied at Leiden physics and mathematics, and he already became a professor in a very new subject called theoretical physics on a very early age of 24. He was a Dutch physicist who shared in 1902 the Nobel Prize with Peter Zeeman, also a Dutch physicist, for the discovery of the Zeeman effect. The main reason Hendrik Lorentz became a well-known physicist was because of his derivation of the transformation equations, which were frequently used by Einstein to describe space and time, otherwise known as space-time. And a few years later, Hendrik Lorentz added time dilation to his transformations, which were called by Poincaré the Lorentz transformations.
Lorentz earned his Nobel Prize for explaining the Zeeman effect, and the Zeeman effect is the splitting of spectral lines in two extra spectral lines, one with a slightly higher frequency than the original one and one with a slightly lower frequency than the original one. And Lorentz's explanation came down to the following. He said that every atom has a charged particle, which he called an ion, but it is actually an electron, but they weren't discovered at that time. And this ion experienced an extra force, said Lorentz, perpendicular to its direction of movement. So, and this force caused the two extra spectral lines to exist instead of only one in absence of a magnetic field. And early 20th century scientists first noticed this effect in the solar spectra, indicating that sunspots were magnetic phenomena.
So, and then to the Lorentz transformations. Well, transformations are used to give the coordinates from one reference frame to give them a measure in coordinates of another reference frame. Well, we have to use the specific time coordinate tau, which is introduced by Minkowski, as we heard, from Germany, and we define this as c times t, so the speed of light times the time that has passed. We use the stationary reference frame with coordinates x, y, z, and tau, and we use a moving reference frame with coordinates x prime, y prime, z prime, and tau prime. For non-relativistic transformations, we use these transformations, and y, z, and tau are the same both in the moving reference frame as in the stationary one, and it's quite logical because if you move, the height of tower doesn't change, or the width of a road doesn't change, and you don't get more time by traveling. Well, x does change, and that's also quite logical, as when you travel somewhere, you come closer to that place, so it comes closer. These are not actually true, as when the speed goes higher, those transformations are more and more wrong. When we take the two reference frames, and when they are at the same point, we flash a light bulb, and as we know, light spreads as a sphere, and we know how fast the light goes, so we know what the radius of the sphere is at a certain moment. So we derive that x squared plus y squared plus z squared is tau squared, and as in a moving reference frame, c is the speed of light is the same, so we derive that x prime squared plus y prime squared plus z prime squared equals tau prime squared.
as we are only looking at the x-axis, we see that y and y primed are both 0 and z primed are also 0. So we find that by subtracting the both formulas that x minus x primed equals tau minus tau primed. And as we know, x doesn't equal x primed, so because of the movement, so we can conclude that tau doesn't equal tau primed. And that's a strange conclusion, as that means that time doesn't change at the same rate for every observer. Well, we have to add a relativistic factor in the transformations, and we can determine this factor, but we are not going into detail here because we have because of time issues, and we see that this factor is the same as the Lorentz factor, which is also named after Lorentz. And we have to introduce two factors, beta and gamma, for the final transformations, as they are frequently used by physicists. We use beta, which is the velocity divided by the speed of light, so it's the kind of a relative velocity, and we use gamma, which is the Lorentz factor, and its formula is shown on the presentation, and we fit those in the formulas we derived from the but we didn't go into detail about those. And we finally get to these transformations, and we'll give an example now for how to use them.
An example, we've got two reference frames. One is relative standing still, that's the Earth, and we've got a rocket, which is the moving reference frame, which is moving with 50% of the speed of light. The rocket goes to a star which is 5 light years away, and the stars go supernova after 8 Earth years. Beta is 0.5, as you can calculate, and gamma is 1.15 approximately, and tau is 8 light years. As seen from the Earth, the rocket is 1 light year away from the star, and the time elapsed is 8 light years, seen from Earth. But as seen from the rocket, from the reference frame of the rocket, x primed equals 1.2 light years, and tau primed equals 6.3 light years. Okay. If the speed of the moving frame increases, beta and gamma will also increase. This means that x primed and x will differ more, and even so, t primed and tau primed and tau will differ more. So you can see there's a difference, and that means length contraction and time dilation exist, but in your normal life you can't experience the effects because you're just nowhere near the speed of light. But when you're nearing the speed of light, these effects become really significant. So when your speed increases, beta and gamma will increase, and therefore the effect will be stronger. Thank you.
Thank you for your information, Netherlands. The GPS signal travels at the speed of light. The movement of the Earth will create an error. To correct it, we must raise the instant.
If the instant is inclined together with the relative movement, the speed of light will never change. It will be an absolute for the universe. This is the form of the Lorentz transformation, and all the relativity effects come from it.
Now the sentence. Lorentz discovered, and you should know your instant rise there where you go.
Now that we